And just a reminder to all learners, if you have any questions during these next presentations, just go ahead and place your questions in the Q&A box at the bottom of your screen, and we will get to them during the last panel discussion.
I think we can probably get started. So hopefully everyone has a chance to stretch during the break. It's been quite a long day. Thank you for sticking through until the last session of this very exciting day of learning. And thanks again to Dr. Lin, Dr. Ying, and the organizing committee. I think it's a great event. We as medical physicists learned a lot by listening to the clinicians, not only in our department, but also other cancer care community. And that's a lot of information and very helpful for us to put what we do in a bigger context. So the next session will be a dedicated medical physics session. So for those of you outside of our radiation oncology team, we physicists are an integral team member of this clinical care team in radiation oncology. And we kind of pride ourselves as the safeguards for the accurate delivery of the clinical care, and also as the envelope pusher for the technology that we use in this field. So today we will have some very exciting talks along both of these lines of duties that we conduct. And first off, let's welcome Dr. Su-Ming Zhou. He's a professor of radiation oncology and also the director of medical physics in our department. And he is going to talk about flash radiotherapy, which is one of the most trendy and also promising and provocative technology in radiation oncology. Let's hear it from Dr. Zhou.
Dan, thank you very much for the introduction. It's an honor for me to give a talk at this symposium with the title Incorporating Intracellular Oxygen Tension into Lethal and Potentially Lethal Model for Flash Radiotherapy. I have no conflict of interest to disclose. Ultra-high dose rate or flash effect is a newly rediscovered phenomenon. With the conventional dose rate we use in radiotherapy, the higher the dose rate, the lower the cell survival fraction, as shown in the upper left graph. But this trend is overturned when the dose rate is above a threshold around 40 gray per second. Cell radiation injury may be significantly reduced beyond the flash threshold. Researchers first discovered this effect in vitro with bacteria and cells in the 60s. Recent in vivo studies reconfirmed this on mice and small animals. This sparing effect is much more prominent in normal tissues than in tumors. Therefore, it has a great therapeutic potential. A human patient was treated with flash RT about 2 years ago. Currently, active flash RT clinical trials are undergoing both in Europe and in the US. There are several competing mechanisms for the root cause of the flash effect. In this talk, I will only focus on the radiation-induced oxygen depletion hypothesis. According to radiolysis, radiation can deplete intracellular tension rho at a rate proportional to dose rate R. Because O2 might fix cell radiation injuries and turn them into lethal, therefore reducing rho could improve cell survival. Intracellular oxygen tension is like the water level in a bucket in this cartoon. Its time derivative is determined by 1, diffusion limited O2 supply rate from its surrounding regions. For example, from capillary systems close to a cell in a living organ. And 2, the cell O2 consumption rate. Usually, these two are in good balance, and the rho is stable. When we irradiate cells, we introduce the third player, radiation-induced O2 depletion. Its rate is proportional to the dose rate R. This radiation-induced depletion effect at the conventional dose rate is insignificant compared to the other two contributions. As a result, radiation will not tip the balance, and rho can be treated as a constant. But the situation can be very different when the radiation dose rate is beyond the flash threshold. Now, this radiation-induced oxygen depletion becomes a significant player in determining rho. Also, due to oxygen depletion in the surrounding regions, the diffusion-limited oxygen supply is reduced too. Combine these two factors, we anticipate some transient dropping in rho with the flash cell irradiation. Cells are the building blocks of life. It's desirable to understand a cell's response to radiation before studying more complex biological systems. Measuring cell radiation survival fraction, SF, versus radiation dose is a favorable approach. Different radiation doses are given to the cells at the defined condition to measure the cell survival fraction as a function of radiation dose. It is a well-known factor that radiation cell survival fraction depends on rho. Cells in hypoxic conditions, the purple line in this, the purple curve in this graph, they have a higher radiation tolerance than cells in aerobic conditions, e.g. the red curve represented in this graph. We can define oxygen enhancement ratio, or OER, as the ratio between the radiation doses DH and DA. Assume the two doses can produce the same biological outcome, in this case, the self-survival fractions in hypoxic and aerobic conditions, respectively. In general, as you can see in this graph, OER is a monotonic increase function of rho. So the higher the rho, the higher the OER. The lethal and potentially lethal, or LPL model, is a successful kinetic model of the radiation cell killing process for conventional dose rate cases. Dr. Curtis invented it in 1986. He postulated that radiation could generate two types of lesions on a cell's DNA strand, i.e., the lethal, potentially lethal lesions. The state transition flow chart is shown at the left. Radiation produces lethal and potential lethal lesions to a cell's DNA strand. Potentially lethal lesions have two possible fates. They can be repaired or they can become lethal lesions. Lethal lesions can't be repaired and will be lead to cell death. Here, NPL and NL are the average number of potentially lethal and lethal lesions. Furthermore, he proposed a mean field theory to describe the time evolution of NPL and NL. For example, the time derivative of NPL is the sum of 3 terms: newly produced potential lethal lesions by radiation, and self-repair term, and also the term transition from potential lethal lesions to lethal lesions. You can see here the production rate of potential lethal lesions is proportional to the dose rate R, and the self-repairing term is proportional to NPL, and this term from potential lethal lesions to lethal lesions is a representative of the interactions between 2 potential lethal lesions from different radiation tracks. And so that's how this factor, the power of 2 comes from. Also, the coefficients of the eta PL, eta L, epsilon PL, and epsilon 2 PL are all cell and radiation source properties. Only eta PL and eta L might depend on intracellular oxygen tension role. The original LPL model has trouble explaining the flash effect. When all model parameters are fixed, the LPL model predicts that the higher the dose rate, the lower the self-survival fraction. So there's no room for flash effect if we do not let the model parameters change during the irradiation time. In Curtis's paper, he briefly discussed the potential possibility of model parameters, for example, eta PL dependence on rho, but no explicit function form was offered. So making it nearly impossible to systematically apply it to flash RT. We propose a modified LPM model for both conventional and flash dose rates. A new pre-lesion state and explicit rho dependence in model parameters are inserted into the original LPL model. The time derivatives of the average number of pre-lesions NPRE is determined by one inflow from the cell DNA, which is produced by radiation and is proportional to the radiation dose rate, and 3 outflows, i.e. self-repair term transitions to the potentially lethal and lethal lesion states. The transition rates of the 3 outflows are all proportional to NPRE. Compared to the original LPL model, the total number of model parameters increased by 2. Next, we want to use the oxygen fixation hypothesis. We propose that the transition rate from the pre-lesions to potential lethal lesions and lethal lesions are proportional to OER. Because the higher the rho, the bigger the OER. Therefore, more pre-lesions will be fixed by O2 and turn into lethal lesion or potential lethal lesion. We can derive the following mean field time evolution equations for the mean number of potentially lethal and lethal lesions in the modified LPL model by combining what we proposed in the last 2 slides. Here, the epsilon pre, eta PL, eta L, epsilon PL, and epsilon 2 PLs are all cell properties. They might depend on the radiation source, but not on the intracellular oxygen tension. Only kappa PL and kappa L might depend on intracellular environment. To inherit the success of the original LPL model, we require our modified LPL model to go back to the original LPL model at the conventional dose rate with no major fluctuations in rho in the cell oxygen level. Fortunately, we can achieve this goal. Typically, for cells, the epsilon PL is much bigger than kappa PL and kappa L. So this is so when the time is not very close to the beginning or the end of a constant dose rate cell irradiation, we can derive this approximate equation for NPL and NL. Their structure, in mathematics structure-wise, almost identical to the original model. So after comparing these two sets of equations, one is for the original LPL model, the right one is for the modified LPL model. We come to the conclusion, in order to have the backward compatibility, this new eta PL bar defined by this ratio should be corresponding to the original eta PL in Curtis' LPL model. The same relationship can be found for eta PL, eta L. And also, I want to point out now, based on our model, we know this eta PL and eta L, both of them will be proportional to OER, the oxygen enhancement ratio. In his 1986 paper, Curtis derived several mathematical results from his original LPL model with a Poisson statistics assumption for the cell survival fraction, and also with the rho as a constant. We can find out, he's basically reached the conclusion that log SF versus dose D has a linear quadratic form for lower dose region. It becomes linear in the high dose and high dose rate limit. The coefficients alpha, beta, and gamma can be linked to the model parameter as shown in these three equations. Combine the last two slides, we can reach the following conclusions for the newly proposed modified LPL model. That is, the alpha is proportional to OER, beta is proportional to OER square, and alpha beta ratio is proportional to 1 over OER. And those conclusions are consistent with experimental observations for low dose region. And by the way, our modified LPL model is the first model to predict this relationship to the best of my knowledge. Now talking about, let's consider the high dose and high dose rate region. We can directly use the conclusion from Curtis' paper. When rho is fixed, the gamma is proportional to the sum of gamma PL and gamma L. Now, as I pointed out in the modified LPL model, both terms are proportional to OER. So now gamma is proportional to OER. So this prediction is very important because now we find out that we can see our OER definition is consistent with the traditional OER definition, and also it is consistent with the traditional definition of radiosensitivity. Here I show you another example This is for a mice cell line called C3H10T1.5. If we use the model parameters obtained by Curtis in his 1986 paper, and also plus the G factors from for water from radionyxes, and also the decay constant for prey lesions extrapolated from previous oxygen after effect experiment, we can compute log SF as a function of dose for any row condition and dose rate. Here, for simplicity, we assumed the oxygen restoration happens very late post flash cell irradiation. For rho equals 0 case, there's no flash sparing effect. And so the two curves, one is from the conventional RT at high dose rate limit. The other one is with the flash dose rate. They are on top of each other. You cannot distinguish them. But for a cell initially in aerobic condition, you can see this yellow one is for a flash RT dose rate. The green one is the high dose rate limit according to LPL model. You can see at high dose, these two curves are separated from each other, and the sparing factor is obvious. So this gives us the hope, and the modified LPL model has the capability to explain the flash RT effect. And due to the time limit, I will not be able to go into the details of this slide. Basically, this is for a single ultra-fast radiation pulse case, just single pulse. We can predict those phenomena. So in conclusion, a modified LPL model is developed that explicitly incorporates rho and is potentially applicable to both conventional and flash radiation therapy. It gives some predictions that are consistent with experimental observations. Further studies are necessary to validate it quantitatively. And the last one is I want to thank my colleagues in the radiation oncology department at the UNMC and the physicists at the UNL for their support and discussion. Thank you.
Thank you, Dr. Zhou, for a very in-depth lecture on flash therapy and also very innovative numerical simulation to and model development to back up the observations. Next, we have Dr. Diane Schott